All right, so factoring, we have a function now. So this is an equation instead of an expression, but it's not an equation that we solve. This is just called a name equation, and it's just names an expression. So we don't have to keep referring to it as the cubic trinomial or hey you. We can call it f, right? Now, just so you know here, nomenclature of functions. F of x is just a fancy name for what we've been calling y. The name of the function is f, okay? Not f of x, although you can refer to the function as f of x if you want. The name of the function is f. The of x just defines the independent variable, okay? So the name of the function is f. We're trying to factor it, and then we want to solve the inequality, what values of x make that function f greater than 0. So step one to factoring is to put it in descending order, right? So let me go ahead and write that as f of x equals, and I've got a 15x cubed plus 2x squared minus 24x, like that. So far, so good. And again, practice your notation, because our test on Thursday is going to have a free response. And since I've been preaching it since day one, you don't want to lose points for lack of notation. All right, now, this is the first time we have an equation that's not an expression. So if I've named it like this and I work straight down, you can either bring down both sides, or you can just bring down the equal sign. You don't have to keep writing f or f of x, okay? But once you establish an equation, you have to keep the equation going. That's new, all right? If I pull out an x, and that's the only thing that's common, I'm left with 15x squared minus 2x minus 24. Okay, now from here, I've got a quadratic trinomial on the inside whose leading coefficient is not 1. You could do target sum, target product if you want. 15 times 24. It's going to be a big number, right? Yeah. Did I? Oh, yep, look at there. There you go. Very good. Man, I'm treating today like a Monday, but you're already well into Tuesday mode, catching the careless mistake. So if you want to split the middle term, you can, but it's going to be a really large number. So this is one where I would kind of say, let's try and do guess and check. The target sum is 2, which if you remember what I mentioned in the video on Friday, if you have a target sum that's a small number, then you want your factors to be relatively close to each other. So I'm going to go off to the side, and I'm just going to, I'm going to do bench work over here. So giving myself some parentheses, remember first, outer, inner, last. I know it's got to be something x squared, something, or something x, something x. So some factors of 15 that are relatively close together. I would choose 5 and 3. Now I could choose those and put those in the slot, not in trial slot, because what's going to depend then is how I pair them up with the factors of 24. 24 has quite a few factors, but are there any that are close to each other? 4 and 6 are probably the closest ones to each other. So it's either going to be a 4-6 possibly, or a 6-4 combo. All right, so now all we're trying to do is get the sum or the difference of the inner and outer to add up to 2. All right, so let's go ahead and try the top row here, the 4-6 combo. The inside would give me 12, and the outside would give me 30, right? 30 minus 12 is not 2. What? 18. That's what 30 minus 12 would be. Yeah, that's not 2. So that's probably not going to work, right? So I'm not going to do that. So is it, or could it be this one? That's 18, and this would be 20. Yep. 18 and 20 have a difference of 2. So I found them. So I know it's going to be pairing up with the 6-4. So let me go ahead and get rid of the temporary stuff. And I'll put a 6 here and a 4 here. And now I just need to concern myself with the SIGN sign. I know because the product is negative, they're going to be opposite signs. And I know that positive 2, the sum is positive. So the larger of the two has to be positive. So that's going to be 5 times 4. which is positive 20, and a negative 18. So there are the two factors. Okay, trial and error, it works. Now I'm going to bring that in over here and list them as, oh, what the heck. The commutative property of multiplication allows me to write these factors in any order, but typically we'll leave them out front. Dun, 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 dun. Okay, so now how do I solve the inequality? I want f of x to be greater than 0. You studied polynomials in Algebra 2. So once you have it factored, remember, off to the side here, I can set it equal to 0. Okay, these are going to give me ordered pairs that are going to be x comma 0. These are also known as x-intercepts. It's where it crosses the x-axis. And you could probably look at them and determine that this is going to be, if you set each factor equal to 0, you're going to get x equals 0. X equals what? If you set 3x plus 4 equal to 0 and solve for x, can you do that in your head? Kind of, yeah. I hope so, right? You would subtract 4 to get negative 4, and then divide through by 3. So that would be negative 4/3. And then you have another one. What would be the root or the 0 or the x-intercept for the factor 5x minus 6? 6/5. Good. Okay, again, that's setting each of the three factors and setting them separately equal to 0. Now, don't forget x, right? Some people overlook that. Now, what do I do with those? Well, I can create a really quick sketch. There's an x and y axis. If I plot those three x-intercepts, x equals 0 is here. X equals negative 4/3. I'm just going to call this negative 4/3. And then x equals 6/5. I'm just going to call this 6/5. Once I plot those three x-intercepts, now I can connect those dots, okay? It's a cubic polynomial with a positive leading coefficient. So what this looks like is it comes in the bottom and it goes out the top, okay? The sign of your leading term always tells you how it exits. The sign of the leading term tells you how something exits. So if the leading term had been negative, then this thing would be reflected across the x-axis. It would exit down to negative infinity. All right, now right now, I don't expect you to know how the graph of a cubic looks like, but if it were just a quadratic, right, positive leading coefficient, you know that means the parabola opens up, and a negative leading coefficient means the parabola opens down. So that's a real quick sketch. Now, is it 100% accurate? No. I don't know how high this local maximum or how low the local minimum go, but that's not important to answering this question. I want to know now for what values of x is the graph of f of x greater than 0? This is y equals 0. What's another name for y equals 0? AKA the what? If you were to plot any point x comma 0, where would those points land? We've already mentioned it. On the x-axis, right? So whenever you have greater than 0, that means above the x-axis. I want to know for what values of x is this graph above the x-axis? Well, let's go ahead and highlight it. This graph is above the x-axis right here and over here, okay? And since you have those x-intercepts found and labeled, you've got the answer to your question. So here is the solution to the warm-up. We're going to say that f of x is strictly greater than 0. That is, the y values of this graph are strictly positive between negative 4/3 and 0 and to the right of x/5. So you could say it like this. You could say for x epsilon negative 4/3 to 0 union 6/5 to infinity. Have y'all seen this notation before with that U It's called the union symbol. This is essentially the mathematical symbol for the word or. This is called interval notation. Interval notation. It has to be from least to greatest. Has to be. And then you need a placeholder for the infinity. The parentheses means non-inclusive. If they were inclusive, that is, if this were greater than or equal to 0, I would include brackets around the three numbers. Okay? Y'all have seen this before. What does this little epsilon mean? We've seen that already this year. X is an element of, or X, the X values that are the solutions belong in this open interval or this open interval. That's basically the same way of saying between these two numbers or to the right of that one. Or you could say this. This is the other way to do it. F of X is greater than 0 for, and then you can list it as an inequality. You could say -4/3 less than X less than 0, or X is greater than 6/5. This is inequality notation. They mean the exact same thing. All right, now whenever you have a connected interval, like the first interval here, it's going to be a number on the left, a number on the right, and the solutions are in between. That's the one where it's written like this with what we call the compound inequality. Smaller number on the left, bigger number on the right. X is physically in between those two numbers, and you have less thans or less than or equal to's. Okay? When you have strictly to the right of 6/5, for interval notation, you need to have an infinity there as a placeholder. And infinity always gets a parenthesis. You can never put a bracket around infinity. But if it's an inequality notation, you could just say X is greater than 6/5. And we assume we head in that direction. Yes, sir.
So for the interval notation, you use the U for or?
Yes. You can, but you don't have to. The interval notation exclusively uses the or, the union symbol. Whenever you're stating it like this, you could use the word or you can write the union symbol. Okay. We typically really only use it with the interval notation. Now, I don't care which notation you end up using, like if you're writing it on a short answer or a free response, but I'll use either one depending on what I feel like when I'm doing a multiple choice question. So you need to be able to read both of them. Okay. All right, now let me give you another inequality to solve on your own now that you have the idea. I want you to solve this one right here. Let's solve, I'll give you an easy one here. X squared, X squared minus 2X minus 8. I want you to tell me where is that less than or equal to 0. Okay. Step 1, you're going to factor this quadratic so that you can find the x-intercepts. Then you're going to quickly sketch a graph so that you can determine if it opens up or down and where those x-intercepts are in relation to that. And then you're going to answer the question. I won't give you a cubic like the warm-up on the test on Thursday, but I might give you one like this. Factor, find the x-intercepts, sketch the graph, answer the question. Hmm? Cubes? The one I drew up here? Yeah, it curved. Curved quite a bit. All right, so on this one, I want to go off to the side, set the inequality equal to 0, okay? Factor it, keep it equal to 0, set each factor equal to 0, which you don't need to show that. You get your 2x-intercepts, okay? Now, the reason I go off to the side is because I don't want to make this mistake. I could go ahead and factor it right here. I can factor it as x minus 4, x plus 2 less than or equal to 0. That's fine. But here's a big no-no. Don't do this. Don't say x minus 4 is less than or equal to 0 or x plus 2 is less than or equal to 0. That does not work, okay? That only works if you're solving a linear inequality. And then you have to remember, if you multiply or divide by a negative, you got to flip the inequality. You can't solve a quadratic inequality or a cubic inequality or anything that's not linear algebraically, okay? So you'd have to stop right here, because once you go past that, now it's incorrect, all right? You don't have to set it equal to 0 to find the x-intercepts. If you want to factor it, you could still tell the x-intercepts from the factored version, positive 4 and negative 2. How do we solve it if we're not solving it algebraically? Graphically, okay? Draw yourself a little x and y axis and put your 2 x-intercepts on there. Here's negative 2, here's positive 4. The spacing doesn't have to be, you know, perfect. Now for a parabola, does this one open up or down? It opens up, right? The leading coefficient is positive. So remember, that tells you that it exits the top, and because it's parabola, it also comes in the top. So here's what the graph looks like. That's all you need right there to answer the question, okay? Now you come back to the original problem and you look at the inequality. I want to know where it's less than or equal to 0. So that translates into where is it below and on the x-axis. Where is it below and on the x-axis? Well, I can see now that that's right here. It's between the x-intercepts, all right? So how am I going to answer it? I'm going to say that the solution then is going to be negative 2 less than or equal to x less than or equal to 4. That would be inequality notation. Or you could say beefy bracket. Well, let's do the x epsilon. And then beefy bracket negative 2, comma 4 beefy bracket. Okay? Either one of those works. That means pick any value of x from this interval or from this inequality, plug it into the original inequality that I gave you, and you're going to get a true statement. Okay? There you go. You cannot solve a quadratic inequality algebraically. You have to solve it graphically or some other way that I'm not going to teach you today. Okay? Finding the x-intercepts is super important. To do that, factoring it is super important. Okay? All right, we might warm up with another one like that tomorrow if we don't quiz. Okay, so let's jump then to 1.3, simplifying and evaluating. Very, very similar to example 1, what we've already kind of talked about. So we can go through this kind of quickly. We have radicals, but they're numbers, okay, not variables. So we can simplify these even if they're not perfect radicals. Like this would be the square root. 32 is not a perfect square, nor is 200, okay? We can only add like terms. That would include having like variables or in this case, like radicals. So how would I simplify the square root of 32 if it's not a perfect square?
Try to get that as much as possible.
Right. And we've seen this one before, right? 32 is 16 times 2. 16 is a perfect square. So just to review, remember, if you can get the prime factorization, and let me do this as 4 times 8, 2 times 2, 2 times 4, 2 times 2. If you can get the prime factorization, then you can simplify the radical easily. Because remember, the root index, in this case, it's implied to be a 2, tells you the price to get out, right? It takes 2 factors on the inside to be 1 on the outside. So I have a pair of 2s, so I can pull 1 out. I have another pair of 2s, I can pull another out. And then anything that's left gets multiplied under the radical. So that's how that one simplifies. Now, the square root of 200 probably simplifies as well. I'm guessing the way this problem is set up is it probably simplifies into something times the square root of 2, right? But if you're not sure, let's go ahead and get the prime factorization of 200. 200 here, boy, what is that? I'm going to say 20 and 10. How about that? And then here I'll say that that's going to be, 5 times 4. 4 is 2 times 2. 10 is 5 times 2. And there it is. I have the prime factorization.
Take out a 2 and a 5.
I can take out a 2 because there's a pair. And then I can take out 1, 5. And then what's left is the 2. So not surprisingly, I'm going to have something square root of 2 plus something square root of 2. And now I'm back to an expression. So I'm working straight down. So I get 4 square root of 2 plus 10 square root of 2. And now this might as well be 4x plus 10x. These are like terms. These are like radicals. Think of the square root of 2 as being those. I have 4 of those plus 10 of those. How many of those do I have? I have 14 of those, right? So this becomes 14 of those. And there's your answer, okay? 14 square root of 2. All right, let's do letter B. The fifth root now. Ooh, getting into fun land. Now look at the second term, the fifth root of 3. That one's already simplified. 3 is prime. So you could think of this as being 1 times the fifth root of 3. More than likely, that first term is going to simplify to something times the fifth root of 3. More than likely. All right. But let's go ahead and try it out with the factoring method. If I can get factors of 96, like 2 and 48. How about 2 and 24? 2 and 12? 2 and 6? 2 and 3. So there is your prime factorization. What's the price to get out? 5. 1, 2, 3, 4. Wow, okay. I do have a set of 5 2s. That means I can pull 1 on the outside. And what's left on the inside? The 3. So the fifth root of 96 simplifies to 2 times the fifth root of 3. Plus 1 times the fifth root of 3. And now I have like radicals. 2 of those plus 1 of those makes for how many of those? 3 of those. Yep. There you go. It's fun, it's easy, it's fun easy. Fun and easy, it's fun easy. All right, questions on that one? We'd seen that already this year. All right, example 2. It says to simplify by rationalizing. Now, let's talk about what rationalizing means. Rationalizing means this. It means getting a simplified radical. Simplified radical to the other side of the fraction. Y'all might have done this before. Hopefully you have, okay? Getting a simplified radical to the other side of the fraction. So if you have a radical, whether it's a square root or fifth root or anything in the numerator, you try to get it out of the numerator and introduce it equivalently into the denominator and vice versa, all right? So let's try that out on example A, because this is probably what y'all practiced back in algebra 2. This is 2 divided by the square root of 3. So I spy a radical. It's a square root. Step 1, simplify the radical if it's not already. Is the square root of 3 simplified? Yes, it is. So how can I then get rid of the radical from the bottom to the top and keep the value of the fraction the same? Well, I'm kind of limited to what I can do without changing the value, right? I can add a clever form of 0, or I can multiply by a clever form of 1. That's what I'm going to do here. I'm going to multiply by a clever form of 1 that is the radical over the radical. This should feel familiar to you, okay? Now, if I multiply straight across, look what I have in the numerator. I get 2 times the square root of 3. And in the bottom, what's the square root of 3 times the square root of 3? The square root of 3 times the square root of 3 is the square. No, they're multiplied. It's the square root of 9, which is what? 3. Yeah. Watch this. Off to the side. There's all kinds of reasons why you should know it's 3. The square root of 3 times the square root of 3 is the square root of 3 times 3. We've had this property already, which is the square root of 9, which is 3. Right? Or you could say the square root of 3 times the square root of 3 is 3 to the 1/2 times 3 to the 1/2. When the bases are the same, what do you do with the exponents? No. Think before you speak. You add them, right? What's 1/2 plus 1/2? 1. You get 3 to the first. Okay? Is 2 square root of 3/3 then simplified? Does anything divide out? No. We're done. It was that easy. It's an equivalent version of what I gave you, except there's no longer a radical in the denominator. It's in the numerator. Okay? So let's look at part B. Now I have the square root of 12 over 4. So what I want to do is ultimately get the radical out of the numerator and introduce it into the denominator. Step 1, simplify the radical first. What does the square root of 12 simplify to? 2 square root of 3. Very good. Because 12 is 4 times 3. And 4 is a perfect square. So I get 2 square root of 3 over 4.
We could do some tricky stuff with timesing it by 1.
Maybe, eventually. But we want to simplify not just early, like we just did, but also often. What does 2/4 simplify to?
Oh, we can divide out and make a 2 on the bottom.
So square root of 3/2. Okay, so all I've done is simplify. I haven't even begun the process of what's known as rationalizing the numerator. But now I'm ready to do that, and it makes life much easier on the back end. So now I'm going to multiply by a clever form of 1, which is, guess what? Square root of 3. Yeah, you always multiply by the radical piece over the radical piece when it's the square root. Okay? And the reason is because square root of 3 times square root of 3 is what in the top? 3. Yeah. The exponent becomes 1, right? 3 to the 1/2 times 3 to the 1/2. We get 3 to the first, which is what we want. And then it's all over 2 square root of 3, and we're done. Now, maybe in algebra 2, you had a hard time walking away from something like that because you were maybe taught that radicals in the denominator are no good. They're fine. They're perfectly fine in the denominator. It depends on what you're trying to do. In this problem, I wanted to get rid of them from the numerator and introduce them to the denominator. Okay? So the square root of 12 over 4 is exactly the same as 3 over 2 square root of 3. Okay. Now, look at part C. I have a variable. That's what's different about this one, among other things, such as this is not a square root. Now, this is a cube root. Okay.
Which makes it a lot harder.
Maybe a lot more fun. Do you think I'm going to multiply by the cube root of x squared over the cube root of x squared? Well, let's see. I can't simplify the radical. Over here, I just multiplied by the same thing over itself. But remember, the whole purpose of that was so that I get rid of the radical. Remember, a radical is basically a what type of exponent? Fractional exponent. So to get rid of the radical means to get rid of the fractional exponent. State that again. To get rid of the radical means to get rid of the fractional exponent. So because this was 3 to the 1/2, multiplying by a 3 to the 1/2 again worked because a half plus a half is a whole, right? So over here, I don't really multiply by the cube root of x squared over the cube root of x squared because that's not going to make it whole. So here's what I want to do.
Would it be cubed root x to the 4th power? Then?
Not necessarily. Write it in fractional exponent form. Okay? The cube root of x squared we know is x to the 2/3. If the whole purpose is to get rid of the radical, which is the same thing as getting rid of the fractional exponent, I have an exponent right now of 2/3. What do I need to make 2/3 whole? 1/3, right? So I'm going to multiply by x to the 1/3 over x to the 1/3, which is really the cube root of x. Now there seems to be a method to the madness to try to make the exponent complete, whole, a nice positive integer. Now let's see, make sure it works. In the bottom, x to the 2/3 times x to the 1/3 is x to the what? 3/3, which is 1. Yeah. And now if I multiply straight across from the top, I get 2 times the cube root of x, which is x to the 1/3. And there it is. That is the answer. Okay? I no longer have a radical in the denominator. I have it in the numerator.
So the answer was doing it too. So the answer was not making it bigger, but making it smaller. Instead of doing
Making what smaller?
the cube root of x to the 4th power, you did times cube root of x to the 1st power.
Correct. Yeah, because the goal was to make the integer a positive whole number. Now, there are other positive whole numbers other than 1, right? I could have made that x squared, but that would be more simplifying on the back end. So you want to make it, you know, as small as possible, but still make it complete, make it whole. All right, let's look at D. This is the 4th root of 1/3. Do we have a radical in the denominator or the radical in the numerator?
Both.
Kind of both, right? To have a fraction under a radical is the same as having a radical in a fraction, okay? So let's go ahead and use our properties of exponents, which is the same as the properties of radicals. It's really 1/3 all to the 1/4 power. So that's really 1 to the 1/4, 3 to the 1/4, okay? Now we'll simplify. What's the 4th root of 1? 1, right? So that simplifies to 1 over the 4th root of 3. That's a simplified version. So now I can clearly see that I end up with a radical in the denominator. So now to get rid of it, I need to multiply by a clever form of 1. Let's see if we could do it without putting it in fractional exponent form. It's going to be some type of root 3. Thanks, Scoob. That's my notification, custom notification. What would we multiply by? The 4th root of 3 is the same as 3 to the what?
3 to the 1/4
3 to the 1/4. If I'm trying to make 1/4 whole, how many more fourths do I need? I need 3/4, don't I? 3/4 then would be raising it to the 3/4 power, which would be the 4th root of 3 cubed. Okay. Now, if you don't want to think about it in radical form, you could keep it in fractional exponent form. I'm just trying to get you to make the connection back and forth between them. So now let's see what I end up with. In the bottom, let's do that first. What is the 4th root of 3 times the 4th root of 3 cubed? Should be 3, right? 3 to the 1/4 times 3 to the 3/4 is 3 to the 4/4, which is 3. And in the top, 1 times anything is itself. So you can leave it as the 4th root of 3 cubed over 3, or, hey, what's another name for 3 cubed? Well, if we keep it in radical form, what's another name for 3 cubed? Is it 9? 27. There you go. And there you have it. The 4th root of a third is exactly the same as the 4th root of 27 all over 3. Okay? Now, I'm going to come up here and insert this little intermediate step because I know some of y'all are like, what happened? If we put this as 3 to the 1/4, it's easier to see that I need 3 to the 3/4, okay, to make it a hole in the bottom. Try to make the jump with me. Try to stretch yourself. We should be able to think easily back and forth between fractional exponent notation and radical notation. They're equivalent. We've already practiced or reviewed that in isolation. All right, let's do one more here and then we'll call it today. Wow, what a fast-paced day. Look on part E. We have 2 terms in the bottom now instead of just 1 term. If you have 2 terms and one of them is a radical, you can't just multiply by the square root of 2 over the square root of 2. Okay? What you have to do is multiply by this. 3 plus the square root of 2, 3 plus the square root of 2. How is 3 minus the square root of 2 and 3 plus the square root of 2 related to each other?
No, they're not opposites.
Conjugates. Good. If you have 2 terms and you're trying to get rid of the radical, you have to multiply by the conjugate over the conjugate. Okay? Here's why. Multiply out the bottom. FOIL. First, outer, inner, last. You're going to get a difference of squares. 3 times 3 is 9. Look what happens on the inside and outside. Minus 3 root 2 on the inside, plus 3 root 2 on the outside. That's 0. And then you're left with negative root 2 times positive root 2, which is negative 2. And on the top, I won't distribute. I'll just leave it like this. And now if I simplify, 14 over 3 plus root 2, 9 minus 2 is 7. And 14 divided by 7 is 2. And whoa, what a fantastic day that was. How's that pace for you? That's a little bit different than the last 2 weeks.
It ended completely on time.
Yeah. All right. The worksheet is out there. I would go today and try to do anything from the worksheet you can that's similar to example 1 and 2. All right. Have a good day. Adios. Will do. You do the same.